In this part of the Neurocomputers and Deep Learning course related to associative memory, we will cover definitions of interpolative versus accretive associative memories, and also autoassociative and heteroassociative memories. We will examine relation between memory elements and the attractors of the recurrent neural networks when they are used as accretive associative memory. One of the primary functions of the brain is associative memory. We associate the faces with names, letters with sounds, or we can recognize the people even if they have sunglasses or they are somehow elder now. In this chapter, first the basic definitions about associative memory will be given, and then it will be explained how neural networks can be made linear associators so as to perform as interpolative memory. Then it will be explained how the neural network can be used as autoassociative memory. Then bipolar associative memory network that is designed to operate as heteroassociative memory will be introduced. As an associative memory, we store a set of patterns, mu k, k is from 1 to capital K, so that the network responds by producing whichever of the stored patterns most closely resembles the one presented to the network. Suppose that the stored patterns, which are called exemplars or memory elements, are in the form of pairs of associations. Mu k is a pair of uk and yk, where uk is a vector in space Rn and yk is a vector in space Rm. K is from 1 to capital K. According to mapping phi, it's a mapping from Rn to Rm, that is from U patterns to Y patterns implemented. We distinguish the following types of associative memories: interpolative associative memory and accretive associative memory. In interpolative associative memory, when U is equal to UR, that is, UR is one of the U pattern in the association. If this is presented to the memory, it responds by producing YR of the stored association. However, if U differs from UR by an amount of epsilon, that is, if U is equal to UR plus epsilon is presented to the memory, then the response differs from YR by some amount epsilon R. Therefore, in interpolative associative memory we have when UR plus epsilon is applied as input, this is U, then the mapping results in YR plus epsilon R. Notice here, epsilon and epsilon R vectors. Epsilon is in the space Rn and epsilon R is in the space Rn, such that if epsilon here is equal to 0 vector, then this implies that epsilon R here is also 0 vector. That means that if we apply a stored pattern, U part, then it results exactly as the Y part of that stored association. This is valid for R from 1 up to capital K. On the other hand, in accretive associative memory, when U is presented to the memory, it responds by producing YR of the stored association such that UR of the association is the one closest to U among all the patterns in the stored associations. That is, the mapping on U results in YR such that UR is equal to the pattern minimizing the distance between SF and U. And we are considering all the patterns UK. K is from 1 to capital K. Among those, we are choosing UK, which results in minimum distance. So for that pattern UR, we are considering the corresponding YR in the stored association. The accretive associative memory in the form given above, that is, UK and YK are different, is called heteroassociative memory. However, if the stored exemplars are in a special form such that desired patterns and the input patterns are the same, that is, YK is equal to UK for K from 1 to capital K, then it is called autoassociative memory. In autoassociative memory, whenever U is presented to the memory, it responds by UR, which is the closest one to U among all the patterns stored. K is from 1 to capital K. That is, the mapping phi on input U results in one of the stored pattern such that this pattern UR is the one minimizing the distance between the pattern and the applied input. We are considering all the patterns. K is from 1 up to capital K. When interpolative memories can be implemented by using feed-forward neural networks, it is more appropriate to use recurrent networks as accretive memories. The advantage of using recurrent networks as associative memory is their convergence to one of the finite number of stable states when started at some initial state. The basic goals are to store as many exemplars as we need, each corresponding to a different stable state of the network. To have no other stable state, to have the stable state that the network converges to be the one closest to the applied pattern. The problems that we are faced with being the capacity of the network is restricted, depending on the number and properties of the patterns to be stored. Some of the exemplars may not be among the stable states. Some spurious stable states, different than the exemplars, may arise by themselves. The converged stable state may be other than the one closest to the applied pattern. Now we are considering neural networks as associative memory. One way of using recurrent neural networks as associative memory is to fix the external input of the network and present the input pattern UR to the system by setting the initial state x, that is x at time 0, is equal to UR. We are setting the initial state to the applied pattern. If we relax such a network, then it will converge to the attractor x star, for which x0 is within the Bayesian attraction, as explained in chapter 2. If we are able to place each mu k, each association stored, as an attractor of the network by proper choice of the connection weights, then we expect the network to relax to the attractor x star equal to mu r. So the attractor becomes one of the stored patterns, that is related to the initial state x0 ur. For a good performance of the network, we need the network only converge to one of the stored patterns, mu k. K is from 1 to capital K. Unfortunately, some initial states may converge to spurious states, which are the undesired attractors of the network, representing none of the stored patterns. Spurious states may arise by themselves, depending on the model used and the patterns stored. The capacity of the neural associative memories is restricted by the size of the networks. If we increment the number of stored patterns for a fixed neural network, spurious states arise inevitably. Sometimes the network may converge not to a spurious state, but to a memory pattern that is not so close to the pattern presented. What we expect for a feasible operation is that, at least for the memory patterns themselves, if any of the stored pattern is presented to the network by setting x0 to mu r, then the network should stay converged to x star equal to mu r. That is, it is desired in associative memory, each memory element to be assigned to an attractor. So, the attractors are the points where the energy surface has a local minimum. So, these are corresponding to the attractors, and to some of the attractors, we are placing the memory patterns. A second way to use recurrent networks as associative memory is to present the input pattern UR to the system as an external input. This can be done by setting theta equal to UR, where theta is the threshold vector whose ith component is corresponding to the threshold of neuron I. After setting x, 0, that is initial state, to some fixed value, we relax the network and then wait until it converges to an attractor x star. For a good performance of the network, we desire the network to have a single attractor such that x star is equal to mu k, final state is equal to mu k, for each stored input pattern uk. We are applying the input pattern and we are reaching the corresponding pair as the final state. Therefore, the network will converge to this attractor independent of the initial state of the network. Another solution to the problem is to have predetermined initial values so that these initial values lie within the Bayesian attraction of mu k whenever uk is applied. This kind of networks will be examined in more detail when considering how these recurrent networks are trained.